All right, I got cut off again there. So let's start this example over again. We're looking at this finite sequence because we know our last term. So term n is 2,916. And we know a is 4. We know r, or we can get r. To get from 4 to 12, we would have to multiply by 3. From 12 to 36, we multiply by 3, which means that r is 3. And what we're looking for is our term number. So term n is equal to a times r to the n minus 1. We're going to sub in the things that we know. So 2,916 equals 4 times 3 to the n minus 1. Again, do not multiply the 4 and the 3 together. We're actually going to divide that 4 out. 2,916 divided by 4 is 729, which is equal to 3 to the n minus 1. What we need here in order to solve this thing is we need our bases to be the same. So if we think of 3 as our base here, we need to know what that exponent is. So we get 3 to some exponent is equal to 3 to the n minus 1. Well, 3 times 3 times 3 a bunch of times will give us 729. And just playing around with that as much as you want to, 3 times 3 times 3 times 3 times 3 times 3, 3 to the exponent 6 is 729. If the bases are the same, 3 and 3, then the exponents have to be the same, which means that 6 is equal to n minus 1, which means that n must be 7. 6 plus 1 is 7. And that means that this sequence has 7 terms. There are 7 terms in, I don't have space, but in the sequence. In the sequence. Another way you could figure this out is just go 4 times 3 is 12, 12 times 3 is 36, multiply it a few more times, and you'll find out that this number right here will be term 7. The exponent part of this, like I said, we'll do that a little bit later, so you'll get a little more practice with that. All right, this one. Term 9 is equal to 768. Term 3 is 12. We need to find a, r, and term n. R right there tells us that this is a geometric sequence, which means that our general term is like this. What we know is this and this. So for term 9, we know that it's equal to 768. So I'm going to put the information we know into this general formula here. So term n, term 9, is 768, and it's equal to a, which we don't know, r, which we don't know yet, to the n minus 1. Well, n is 9 because this is term 9. So 9 minus 1. So 768 is equal to a times r to the exponent 8. We also know that term 3 equals 12. So I'm going to put that into the general one again. So 12 is equal to a times r. Term 3, so the exponent will be 3 minus 1. So 12 is equal to a r squared. Now, in the earlier video, I mentioned that there were going to be 2 ways to solve something, and then I only showed you one. The reason I only showed you one is that the other way to solve it is what we're going to do right now. So with that one, we were calculating the common difference d, and we used what I called the quick method. The other method is using either substitution or elimination. So think back to grade 9, I believe it was grade 9 or 10 math, and you learned about substitution and elimination. So you're going to use that here. So we have 2 equations with 2 unknowns, which means we can definitely solve for both of those unknowns. So for this one, I'm going to rearrange both of them actually so that I have a by itself, so then we can set them equal to each other and find out what r equals, and then from there find out what a equals. So here we have a by itself will be 768 divided by r to the exponent 8. And for this one, a is equal to 12 divided by r squared. These a's are equal to each other because they're both in the same geometric sequence. So we can set these equal to each other. So I'm going to set equation 1 equal to equation 2. Set 1 equal to 2. Don't have a whole lot of space here, so I'm using what little space I have. This one is equal to this one. And again, lack of space, so I'm going to be working horizontally. It's best to work vertically. I'm going to rearrange so my r's are on the same side, so I'm going to cross multiply and divide a little bit here. So we get 768 divided by 12 is equal to r to the exponent 8 over r squared. 768 divided by 12 is 64 is equal to r to the exponent 8 divided by r squared. When you were dividing these powers with the same base, you subtract the exponents. So 8 minus 2 is 6. Now the way we solve this thing is just like something squared and something square rooted are the opposite of each other. Something to the exponent 6 and something to the 6th root. That did not work out well. The 6th root with a 6 there is equal to r. And just like when we square root and we have to have the positive and negative answers, same idea here. Because these things could pair up, r times r times r times r times r times r, 6 times will give us 64, and each of those pairs of r's could be positive or negative. So the 6th root of 64 is either 2 or negative 2. And I've completely run out of space here, so we get r equals positive or negative 2, plus or minus 2. I'm going to have to erase all of this in order to continue this example. Actually, maybe I'll just put it on this slide right here. All right, so we have r could be plus or minus 2. Let's start with case number 1. If r equals positive 2, then we would put that back into our equation. Term n is equal to a times r, which is 2 to the n minus 1. And now I'm going to take some of the information that we already knew, which was that term 3 was equal to 12, or term 9 was equal to 768. I'm going to go with term 3 equals 12 because they're much smaller numbers, easier to work with. So 12 is equal to a times 2. This was term 3, so n is 3 minus 1. So 12 equals a times 2 squared. 2 squared is 4. So 12 equals 4a, or a equals 3. Case 2, I'll do over here, was if r was negative 2. Same idea, we're going to put all of this information into our equation. So 12 equals a, which again we don't know yet, times r to the n, which this was term 3, so n minus 1 is 3. And you'll notice we get a to the negative 2 squared, which will again lead us to a equals 3. So in either case, which is good, a equals 3, because negative 2 squared is positive 4, 12 divided by 4 is 3. So either way, we get this. So the question was asking us to find a, r, and term n. Well, we found r, it's either plus or minus 2. We found a, which is 3, and term n we can get now using a and r. So therefore, a is 3, r is, we'll start with the first case, 2, and term n is equal to 3 times 2 to the n minus 1. Or we have a equals 3, r is negative 2, and term n is equal to 3 times negative 2 to the n minus 1. Either of those are possible. Okay, so that's the end of all the geometric sequence examples, and now I have a few more that are recursive. So they could be arithmetic, they could be geometric, or they could be something else. But they are a sequence as in a list, a list of numbers, not a series. That's something slightly different, and we'll talk about that another day. All right, here's the first, write the first 4 terms of this sequence. So term 1 is negative 1, term 2 is 1, term n is equal to 2 times term n minus 2, which would be the term 2 before the one we're looking for, plus 4 times term n minus 1, which would be 4 times the previous term, and n is greater than 2 in this case because we've already been given term 1 and term 2. So first 4 terms, well, we already know the first 2. They're already given to us. So we actually only have to find 2 more. So term 3 is equal to 2 times term n minus 2, and n is 3 here, so 3 minus 2, plus 4 times term n minus 1, which would be 3 minus 1. And again, remember these are subscripts. Don't write these 3 minus 2 and 3 minus 1 bigger. Don't write the 2 and the 4 smaller. You will get yourself confused. So this is 2 times term 3 minus 2 is 1. So 2 times term 1 plus 4 times term 2, because 3 minus 1 is 2. Term 1 is negative 1, and term 2 is 1. 2 times negative 1 plus 4 times 1 gives us 2. So term 3 is 2. Term 4 equals 2 times term 4 minus 2 plus 4 times term 4 minus 1. So this is 2 times term 2 plus 4 times term 3. Term 2 is 1. Term 3 is 2. And 2 times 1 plus 4 times 2 is 10. So term 4 equals 10. So term 1, therefore, let's summarize this. Term 1 is negative 1. Term 2 is 1. Term 3 is 2. And term 4 is 10.